Hey folks, welcome to this episode on predicting products. In this episode, we're going to be looking at synthesis, decomposition, and combustion reactions. So why is it important in knowing how to predict products? Well, first of all, if you're walking through a lab and you're trying to think of what chemicals to mix, it's actually quite important to know what's going to be created. You can make something spectacular in terms of a pyrotechnic kind of display, or you can create chlorine gas, which might really injure you. So knowing what chemicals you're mixing and knowing what kind of products are going to be coming out of it is very important. But not only that, there's also an economic factor of this. If you're a chemist or you're a chemical engineer and you're saying, I need to create this product with these properties, you're going to have to know what reactants to start with. So knowing what reactants and what they make is also going to be important for creating that final product. So general steps for predicting products. First of all, figure out what kind of reaction it is. If it's two individual elements, you know that it might be a synthesis reaction, so run with that. Then rearrange the chemical names if you're dealing with a word equation, or the chemical formulas, the symbols, if you're dealing with actual chemical formulas, that would match the general formula of the reaction you chose. So in terms of synthesis, if you had two simple elements, you'd create one compound at the end. If it was single displacement, and depending if it's a metal or non-metal, you would rearrange them however you needed. Next thing, you have to make sure you're determining the correct formulas. The correct formulas are absolutely key, because if you don't have the correct formulas, your balancing is going to be off and everything is going to be incorrect. Finally, balance the skeleton equation. So some tips that you should remember is remember Hofbrinkel. Hofbrinkel are elements that are diatomic when by themselves. That's the key thing here, is that when they're by themselves. When they're in a compound, you have to look at the oxidation states or the charges from the other things they're bonding with. So for example, we'll look at it in the bottom here. When you're looking at ionic compounds, always use this cross method to determine the subscripts, okay? So the subscripts don't transfer automatically from one side to the other. So in this case, aluminum chloride, you would have Al and Cl. This is going to be 3 plus, this is going to be 1 minus, cross, and you get AlCl3. So first things first, notice how it's not diatomic, it's not Cl. Cl is part of Hofbrinkel here, but Cl is not by itself, it's bonded with Al, so it's determined by the oxidation state of Al. Now this is, let's say there's some kind of other reactant here with it, and then we have on the product side, we have sodium chloride. Well, it's not going to be NaCl3. That's not the case. What we have to look at is the oxidation states of the two bonding atoms, so Na and Cl. This is 1 plus, this is 1 minus, we cross and cross, and we get NaCl. Okay? So the subscripts don't transfer from one side to the other. You have to figure them out every single time. So first things first, let's look at decomposition reaction. This is kind of a general way of trying to figure out what the product is going to be. Now, a general decomposition reaction always starts off with one product, and it breaks down. So in this case, we have ammonia, NH3. So once we know this, we can break it down into simple elements. So the simple elements are nitrogen and hydrogen. So I just listed them here individually. Now I checked these, and I want to see, are these diatomic? Are they included in this Hofbrinkel? Well, here's hydrogen, here's nitrogen. So we're going to put them as N2 and H2, and they're going to be gases. And so here we have our skeleton equation. One thing that's wrong is it doesn't suit the law of conservation of mass, so we're going to have to eventually balance it. So there are some exceptions that we talked about. Initially, we spoke about carbonate and how it breaks up into a metal oxide and CO2. But there are some other exceptions that you may see throughout this course and throughout your future studies. This most simple is any kind of binary compounds, ones that we'll mostly be dealing with. They just break up into their simple elements, just like we'd had a previous example with ammonia. Carbonates, again, break down into CO2 and their metal oxide. If you deal with a chlorate, so ClO3, 1 minus, this breaks down into its metal chloride, so barium chloride, okay, metal chloride, and oxygen gas. Hydroxides, on the other hand, they break up into the metal oxide, so metal oxygen, and the other two hydrogens and one oxygen will create this water. So when we look at this formula here, we have OH2. That means we have two hydrogens and two oxygens. One of these oxygens moves with the metal, and the other oxygen and two hydrogens form the water. And oxyacids, here we have phosphoric acid. This is phosphate. That suffix ends to ic, phosphoric acid. it breaks up into its non-metal oxide, so the P and the oxygen, okay, and the non-metal having the same valence, and then we also create some water. So let's look at an example here. Sulfuric acid decomposes into something. Let's figure out what those products are going to be. So in this case, what we have is we have an oxyacid. We have sulfuric acid. This is 8, so this is sulfate. So first of all, let's figure out what this formula is. If this is sulfate, that's going to be SO4. We have to have hydrogens because it's an acid, so 1 plus, 2 minus, we cross, and we get H2SO4 aqueous. Now that breaks down. Now, what is it going to break down? Well, it's not a binary compound. It's not simple things. It actually has to follow through with a rule. If you look back, so these oxyacids break up into their water. It breaks up into water, and it is kind of non-metal oxide. So it's all based on this sulfur. So this sulfur is going to create a non-metal oxide, and we're also going to create water. So first of all, I'm just going to write down the water here. H2O, and that's going to be liquid. Now, what else am I left? Well, I took 2 of the hydrogens out. Okay, I took 1 of the waters out, so now I only have 3. So what I'm left with on this side is now going to be SO3. That's it. Make sure that we're balanced. We have 2 hydrogens on this side. 2 hydrogens. This is going to be a gas. 1 sulfur, 1 sulfur. 4 oxygens. 1 plus 3. We have 4 oxygens. Okay. So try your hand at these ones over here in decomposition. So follow the steps, figure out what your reactant is, and see if it follows any of those special rules to break down. So go ahead, pause the video now. We'll be back with the answers. So welcome back. Here are the answers. Potassium carbonate breaks down into potassium oxide and carbon dioxide. So the carbonate, again, that breaks down into the CO2. Now, one thing to remember is that if we know that we have a carbonate, we're going to break into CO2. We're going to be using 1 of the carbons, and we're going to be using 2 of the oxygens. That means we only have 1 thing left. So here we have K2O. Okay, we have 2 Ks, 1 O left, K2O. Now, again, that will also be created through our oxidation states. This is 1 plus, this is 2 minus, cross, and we get K2O. Rubidium chlorate decomposes. So when chlorate decomposes, it's a metal chloride and an oxygen. So here we have our oxygen, we have O2 there. Okay? And our metal chloride here, well, if it's a metal and a chloride, we have rubidium as our metal and chlorine as our chloride. This is going to be 1 plus, this is going to be 1 minus, cross, and we got RbCl. All right, our next type of reaction is a synthesis reaction, and this is where we have 2 simple reactants creating a 1 compound. So here, to start off, we have oxygen and aluminum. Now, it might not be in the order that you're used to, but it really, when you're presented with reactants, it doesn't really have to be in any order in the kind of mainstream lab environment. On a question, it usually will give you the metal first and the non-metal, but you might not observe that actually in the lab. So here we have our oxygen gas and our aluminum solid. Now, when we combine these elements, we will be creating 1 compound. So we should have 1 product. So what we've done is I've written the metal first, the aluminum. Okay, regardless of what the order is like over here, I wrote the metal first in the product and followed by the non-metal. So here, after that, once we have our order of elements, we now have to figure out what the subscripts are, and we use the cross-down method. So once again, we have Al and O. This is going to be 3 plus, this is going to be 2 minus, we cross, and we get Al2O3. And finally, the last step is just to balance. So some synthesis tips. Synthesis is the opposite of a decomposition. So a lot of these tips are the exact same as the decomposition, except in the reverse direction. So whenever we have 2 simple elements, we create a binary compound. Okay, so we do that. Once again, to figure out what these subscripts are, you have to use the cross-down method. Don't be fooled that because it's F2 here, it's going to be F2 here. This is because it's diatomic, and this subscript is because Sn has a charge of 2 plus. Okay, so don't be fooled, they don't carry over from one side to the other. In the case of a metal oxide and carbon dioxide, you're going to form a carbonate. Something with oxygen and chlorine, a metal chloride, you're going to get chlorate. So you can see that this is the exact same except the opposite direction. Here, when we have a metal oxide and we have water, we're going to form a hydroxide. And in this case, when we have this non-metal oxide and water coming together, we're going to form the oxyacid. So here we have sulfur and silver reacting. So let's see what we can get from here. Now, the first thing we have to know is what are the symbols for silver and sulfur. Well, silver is Ag, and sulfur is S. However, S exists as a polyatomic ion, and it's not in the terms of like SO4, not sulfate, but sulfur itself has a polyatomic structure. And just like diatomic, for example, H would be existing as H2. If you remember, phosphorus exists as P4. Sulfur exists as S8. Now these are solid and solid. So here we have our two reactants. Now what are they going to produce? Well, we're going to always write the metal first, Ag. Write the non-metal second, S. Okay. And now we have to figure out what our final formula is going to be. Remember that the charge of Ag is 1 plus and S is 2 minus. We cross, and we're going to get Ag2S. Okay? Now here we need to balance. So in this case, we have 8 sulfurs. We're going to put an 8 over here. 2 times 8, that's going to give us 16 silver atoms. So again, pause the video, try to your hand at these ones over here. We have aluminum bromine reacting, and then calcium oxide plus water reacting. So make sure that they fit one of those tips in the synthesis. They might be able to form a binary compound. They might form oxyacids. Follow those and see what you can get from here. Remember to balance at the end. All right, pause the video. All right, welcome back. Here are your answers. So again, we have aluminum and bromine. Now remember, bromine is part of Hofbrinkel, so it's going to have this Br2 configuration. And to figure out what we have here, so again, we have to figure out our formula. We have Al and we have Br. This is going to be 3 plus, this is going to be 1 minus, so we cross, and we get AlBr3. In this case, this follows one of those rules where if we mix a metal oxide with water, we're going to get a hydroxide. So in this case, we have calcium oxide reacting with water, and we get CaOH2. Now, our last type of equation that we're going to look at here, types of reaction, is a combustion reaction, where we start off with a fuel, and that's usually in the form of a hydrocarbon or a carbohydrate. A hydrocarbon only has carbon and hydrogen in them. A carbohydrate has carbon, hydrogen, oxygen. Sometimes it also has nitrogen. Sometimes it can also have sulfur. So we can start off as these as our fuels. Now, in any combustion reaction, we have to combine it with oxygen. That's one of the things necessary for a fire. And in complete combustion, we are always producing the same products, carbon dioxide and water. So it's very, very simple. We're really just going to be focusing on complete combustions in this course. So your products will always be the same, and one of your reactants will also be the same because we also need that in any kind of combustion reaction. And finally, like always, we balance. So there are some exceptions here, or an extension really. If your hydrocarbon or a carbohydrate contains nitrogen or sulfur, you will have another product being made. If it contains nitrogen, you're also going to have this NO2 being produced. And if you're containing sulfur, you're going to be producing this SO2 along with your regular CO2 and H2O. So here's an example. Here we have methanol combusting in the presence of oxygen. So here we have CH3OH, and this is going to be a liquid, plus oxygen, to form our two products, CO2 plus H2O, all of these being gases. All right, that looks a little bit off there. Let me just fix that. All right, now here we have our reactants and our products. It's very simple. Okay, the only thing that we need to do is balance this. Now, if we look at balancing and we say on the left side we have 1 carbon and we have 4 hydrogens, the first thing we probably want to do is put a 4 over here to, put a 2 there to look at the number of hydrogens. However, when you do this, what you have to remember is if we make this oxygen even, and this is already an even oxygen, we have to have an even number of oxygens on this side. But we don't. We have this lone oxygen here. Remember, any number that we put in front of a 2 will always make an even number. So we have to do something to this oxygen to make it even. So right away, I know that I'm going to have to double up. I'm going to have to double up over here, okay, which means that I'm going to have to put a 4 over here. I now have 2 carbons on here, so I'm going to put a 2. On this side, I have 4 oxygens plus 4 oxygens, so altogether I have 8 oxygens. In this equation over here, I already have 2 oxygens here. So how many oxygens do I need? We can kind of solve for x here. How many oxygens do I need? Well, 8 minus 2 will give us 6 oxygens. 6 divided by 2, because there's 2 oxygens in this compound, would give us 3. So, again, go ahead, pause the video, and try to create the combustion reactions for these reactants. We'll come back in a few moments. Pause the video now. So once again, here are the answers. No tricks here in terms of any nitrogens or sulfurs. Straightforward. Here we have ethanol and ethine. So here's ethanol, ethine. They both undergo a complete combustion, and all you have to do is really balance these ones at the end. So that's it for this episode. Thanks very much for watching. See you soon.